In this tutorial, we're going to investigate some techniques that can be used to reduce our memory footprint. Now, your mileage may vary with this. In my case, I found that it did not significantly affect performance, but that could be to do with the bottleneck in my program being something different. But here's what we got at the moment. I've got these vertices, and their memory layout is as such. We have a vec3 for position, a vec2 for texture coordinate, a vec3 for normal. I'm using standard vectors with standard single precision floats. That's 32 bytes per vertex. Let's go ahead and have a look at that. Okay, so here we go, 165 frames per second, and yeah, 150, something like that. We've got some performance, and here's our scene. We've got all the objects. Okay, so this is all well and good, but the question I'm asking today is, can we represent these vertices with fewer info, fewer bytes? And the answer is yes. And I'm curious, let me know in the comments right now, how many bytes do you reckon I'm going to be able to get this down to? So as a first approximation, I'm going to have a look at half precision floats. So OpenGL gives us some options when we're sending over vertex data, and one of those is half precision floats. The idea is we can specify our data in a half precision format, send that over, and then on the shader side, it gets automatically converted to full precision floats. So although the GPU is not doing half precision math, which would be faster, for reference, Apple GPUs can actually support half precision math natively, and it's been found that it about doubles the performance. But unfortunately, even though we don't have that, we still have the increased memory bandwidth of quickly fetching data. So, as a refresher, floating point numbers are represented by packing a number of bits together. Similar to scientific notation, we have a sign, a mantissa or a coefficient or a fractional part, and then we also have an exponent. Now, half precision floats are similar, they just use fewer bits to hold the mantissa and exponent. So, conundrum. C++ does not have native support for half precision floats. So how do we store them? The solution is to pack the bits manually into a permissive data type such as a uint16. And that's fine because we're not doing any math on these things. We're just packing in the data, transmitting that to the GPU unpacks it on its side. So what we could do is we could go in and work this stuff out manually, but in this case I've deferred to people smarter than myself. So in the provided code, this is the code that I'm using for conversions. This was sourced by this Stack Overflow discussion here. But yeah, so I've got that. So let me just go through, and there is going to be a little bit of just modification here. So this is my vertex lump. This is all my data that I'm putting in. I'm now going to switch that over to store half precision floats. And then I'm just going to go down. There's basically two functions that I'm really interested in. And they are, well, first up, this is going to need to be, it's going to be just a fair amount of fiddling around here. And I go with the linting approach of debugging, is I just let the static analysis pick it up for me. But I'm just changing all of these over so that my vertices are storing uint16s basically. Okay, so it's at this point here, I'm going through, I'm doing all this loading, and then in this read corner function, that's the point at which I'm stuffing the data into the collection. So what I'm going to do is I'm going to use that float to half function on each of these, get them in there. There we go. So then I'm just going to go to the point at which we finalize everything. And now for the total number of bytes, I'm going to multiply this by the size of that uint16, which of course is half the size of a float. So now we're representing every vertex with 16 bytes. And similarly, our offsets are going to be halved. And then here where I specify the format, that will be, we can use GL half apple. What's a half of an apple? You got to eat it quickly, otherwise it goes brown. GL half float. Okay. I'll just quickly double check through this. I don't want to get any of it. Well, it doesn't matter, does it? Okay, so all good. We've converted the floats to half precision. We've sent that over. We don't need to do anything on the shader side. So we've gotten that down to 16 bytes. Let's do the final round of error checking. Okay, so it appears as though something has gone wrong. Yeah, okay, this might be it. So after I load everything in, I then blit it over to the big vertex lump basically. And I think I had the wrong data type there. Let's see how that goes. I hope this is it. Ooh. There we go. Another situation. Be careful when you copy paste. Okay, so there we have it. And is that an improvement? About the same? There is some weird flickering thing going on, but I suspect that may actually have to do with the way I've been sort of bundling a bunch of storage buffers together and maybe running into some limits or something. So I'm going to leave that weird flickering effect for now and say, there we have it. We've got the data. We've got it from 32 bits down to 16. So that's pretty cool. Then the next question is, can we do better? And the answer is yes, we can. So both of the normals and the texture coordinates are expected to be normalized. The normals are expected to be in the range -1 to 1, and the texture coordinates are expected to be in the range 0 to 1. In other words, it's sort of the same as just having a fractional component, having no exponent. So wouldn't it be great if we could just send the fractional data? Turns out OpenGL actually allows for this. We can send a byte of data and then tell OpenGL that the byte represents normalized data. OpenGL will then do the same thing. It will convert that byte into a signed or unsigned float as requested. So the conversion functions for these bytes are actually quite simple, because OpenGL's convention is basically just to take, like if I have an unsigned byte, then 0, there we go, 0 maps to 0 and 255 maps to 1.0. That's how it works. So if I just take in a float, which I'm expecting to already be in the range 0 to 1, multiply by 255, turn that into an unsigned character, then that gives me the 0 to 255 range. And then similarly, if I want to have signed characters or signed floats, then I'll just multiply by, we'll say 127, because what this will do is it will map, it will map -127 to -1, +127 to 1, or something very close to 1, which is perfectly fine. So that's the basic idea. And I'll go ahead and start looking at the memory layout here. So the way this works, half float, we can keep that. Here I'm going to go for texture coordinates. That'll be unsigned bytes. So if I look here, unsigned float will have 6 bytes. 2 unsigned bytes will be 2. And then 3 signed bytes will be 3. So we'll have a memory stride of 11 bytes in total. And then these will be GL bytes. Now, something which is very important, is this next argument, which is whether the data is expected to have been normalized. So if I send through, let's say, an unsigned byte, and I say this has not been normalized, then we just go with C conversion. So 0 maps to 0.0, 255 maps to 255.0. On the other hand, if we say, hey, this stuff is representing normalized data, then OpenGL says, yep, no worries, and it does that 0.0 to 1.0 conversion, if that makes sense. So this is just telling OpenGL, okay, we want this to be fixed precision normalized data. Okay, so that's the basic idea, but I am going to need to do a bit of refactoring work now. So for my vertex lump, instead of just being uint 16s, it'll be bytes basically, so a collection of unsigned characters. And then on the other side, okay, so our vertices again going to be bytes now, and then I'll be again mem copying some bytes. And the size of a byte is 1 byte, so we don't need to worry about that. And this is a part of the video which is sort of boring because I am just copy pasting a lot. Okay, so when I do this texture coordinate stuff, I want to go float to ubyte. And then when I do the normal coordinates, I want to go float to byte. Yeah, why not? I'll just do that, that's fine. Right, so then the other exciting bit is how am I going to handle this half precision float to bytes? Well, here's what I'll do. First up, I'll get this as a half precision float. And then just to be super explicit, I'm going to extract the lower and upper bytes of it. So I'll just bit mask off the lower byte, and then to get the upper byte, I'll do the same thing. So I'll take the number, shift it down by 8 bits, and then bit mask that off, and that'll get the upper byte. And then I'll need to push both of those bytes on. How many times can I say byte? Okay, so I am going to run into problems here, and the reason for that is that I'm sort of hacking this. I should not be doing this, but this is what I'm doing. Originally, I had 8 elements representing every vertex, so I could just take the number of vertices, divide by 8, and that was the number of, the number of vertices. But now, because I'm doing it in bytes, I've now got 11 bytes per vertex, so I'm going to have to divide by 11. So don't do this in real life, but this is just a tutorial. I'm just having fun. Right, so let's see how this goes. Oh my goodness. Can you see it? Okay, so I do not need to convert these things to half precision. That's a boo-boo on my part. Don't do that. That's embarrassing. There we go. So yeah, as you can see, the texture coordinates look fine, the normals look fine. Something really, really funky is going on with the visibility. But like I've said, I suspect that's not to do with this. I suspect that's some other error that I've made. But yeah, so there we have it. We've reduced from 32 bytes down to 11 bytes with some strange glitches. So then the next question is, can we do better? So remember how we sort of took the exponent for the normals and the texture coordinates and we ignored it, we threw it away. The reason is we sort of expected the exponent to be 1. We expected the magnitude to be 1. So for our purposes, we can conceptualize the exponent of a floating point number as representing its magnitude. And this sort of gives us a hint for how we can further compress the data. Look at the positions. We have 3 components, X, Y, Z, for every position, and every one of those positions, the X, Y, Z components have roughly the same magnitude. Like if we find a common magnitude for the X, Y, Z components, take that out, then we can multiply it back in. But does that make sense? It's roughly the same for each of them. So what we could try is we could try decomposing a little bit further. So let's say I've got the position here. I want to get the magnitude of that position. So far, so good. Then I'm going to normalize the position. And I'm going to throw that data in. So I'll go float to byte. And then in addition to that, I'm going to push the magnitude. Okay, so what I've done, like I said, is I've taken this position, I fetch its magnitude, normalize it, and then push all that info on. And then on the shader side, I'm going to recover that info. So if I just go into my shader, I'm going to change my layout. And I can just use that magnitude here to scale up the vector, and that will, in theory, recover it all. So then what I'll need to do is, because I'm pushing on that extra byte for the magnitude, I've now got 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 9 bytes per vertex. So I can go back to my finalization, and now I've got a stride of 9. So this is a unsigned. And just so I don't get into trouble, I should go back and convert that properly. So what I'm going to do here is I'm going to keep the normalized argument as false for this attribute, and that will attempt to push through the actual number. So I'm representing scales from 0 up to 255, but that will be perfectly fine for my purposes. So then I'll go through and I'll do the rest. So again, this will be byte data, which is normalized. Okay, cool. So let's have a go at this. It's like there's an edge case I've neglected to do. I think it's the divide by 11. Yeah. I've now got 9 bytes per vertex. Again, please don't do this. Please come up with a more semantic way of handling it, but I'm just hard coding it. I think I've worked out the edge case. So what's happening here is with these like float to U bytes and float to bytes, this is with the expectation that the bytes are normalized, which then squeezes them to the range sort of 0 to 1. But in the case of this magnitude, I actually want to pass in the actual number. I don't want to multiply that up by 255. So if I just put that number in, the fact that I'm pushing onto a vector of bytes will force it to be in integer form. This really is unscripted today. Okay, there we go. So positives, we're using less bytes. Negatives, we have a problem. And this problem it's a little subtle, especially like in the case of this square, right? This cube works perfectly fine. This block works perfectly fine. But then if we go over to, maybe not this thing, but some of these blocks, like, yeah, we can see it with the tree, I think, they seem to just get weirdly squeezed. So the issue here is that we can pass through floats as numbers and they'll get converted, but they only get converted to whole numbers like 1.0, 2.0, 126.0. And that's not going to work. when we've got decimals. It's not going to work very well. So what I'm going to do is, for the magnitude, I'm actually going to have a proper float. Now, in terms of a vertex attribute, having a proper float is really bad. It takes a lot of memory. But in terms of, well, I won't even say that. The question is, should we be declaring the magnitude on a per vertex basis? The answer is no, because it's also perfectly valid to take a mesh and find the size of the whole mesh, normalize the positions on that mesh, and then scale the whole mesh up by whatever the mesh's size is. And then also, if we look at the acceleration structure, which is the data payload that we're sending through on a per mesh basis, it actually has some free space. So all of this is to say, I'm going to leave this, and when I load in my meshes, I'm going to do that in a 2-pass process. So if I look up here, I'm going to load the file in 2 times. The first time I'm just going to look through and sort of store the data, but not load and not create anything. And then the second time I'm going to look through and actually triangulate the faces. And the reason for that is that I'm going to query the size of every position that I see and save the largest magnitude, if that makes sense. Now I'll deal with that in a second, but I also need to deal with the AABB. So I'll just go over to my config file where I've defined this struct, and then instead of this vec4, I just did this vec4 for convenience, really. I'm going to pick out the magnitude, and I'll save that in the AABB. So I'm going to do something very similar on the compute shader. This is not super interesting, I get it. Okay, so as for how this magnitude stuff gets used, well, I'll need to take in the magnitude as an argument when I read the corner. Okay, and then down when I read the corner. I can take in the magnitude of the whole model, not just the individual vertex, and we have the guarantee that all of these vertices components will be in the range 0 to 1, because this magnitude is the maximum size of the entire model. I don't know, I'll get to that later. In terms of this data that we send through, I'm going to get rid of this now. So the final answer, by the way, is I'm getting this down to 8 bytes per vertex. Okay, so I'm a little lazy, so my debugging method, I understand there's a lot I still need to do. I'm just going to run this and let it work out what I need to do. Okay, so this is in the camera, and it's just because I changed this from a vec4 to a vec3. I think that's it, and then I'm just going to go over to my vertex shader, and like I said, we don't have this option anymore. So I'm not going to apply that scale, but in the compute shader, I do have access to the size of the model. So first up, I'm going to need to, as before, where am I? I think that's fine. And then right down below, after I've done all my visibility detection, I'm going to throw in that scale transform. So I've got these functions here which I can use to generate transformation matrices. I'm just going to take the current AABB, fetch its magnitude, and use that to bake into the model transform. And it's important that I multiply this on the right so that it is performed before all the other operations. Yeah, let's just click this and see what it does. Interesting. Probably it's the thing that I've been complaining about all video. Passing in the incorrect number of vertices. Yeah, and also I should not be sending that data through. There we go. Please, please. Okay, right, so there we have it. We've got everything. We've compressed this down from 32 bytes per vertex to 8 bytes per vertex. Given how extreme that compression is, I think this is pretty good. But it's definitely not perfect. So if I go over to some of these more detailed models, apart from the weird popping, which again should not be happening, we can see that obviously the positions are less accurate, they're more coarse. This is more of a PS1 graphics style look, and there is some Z fighting caused by the inaccuracies in the positions. So this is not a perfect technique. A lot of these models look okay from a distance, but look sort of like Minecraft up close. But you know, for I guess I'll say these compression techniques exist on a spectrum, and the more aggressive we get with our compression, the more visible it is. And your mileage may vary. You may be in a situation where compressing the vertices a little bit makes a big difference for performance. For me, I think the bottleneck in this program is just the sheer amount of stuff that needs to be drawn. But anyway, that'll be it for this video. I hope you enjoyed. This is longer than I normally do, and it's definitely more diffuse than I normally do. But sometimes I like to have these videos where I run through a number of stages, show what works, show what doesn't work, and hopefully you feel more informed after watching it. But yeah, have a good one, and I will see you again soon. Bye. Hello, how's it going? I know it's been a while since I've done one of these Patreon readouts. It is not super fun watching the numbers go up, go down. It's like a health meter in a video game, except it's real life. But I am community supported, and you guys are salt of the earth. Everything you give, like it does. I know I sound sick. I'm not putting this on. I really do appreciate it. It's very cool. Thank you, my dudes. If you would like to support me, it's $2.50 a month. No more, no less. But without further ado, really big thank you to Antonin Carret, Declan, Endelon Studios, sorry if I say this wrong, Juan, Valsvilla, sorry, Mathieu Duric, and Moim. Thank you so much. It really does mean a lot. And yeah, here's to many more happy times. All right, cheers.